All right, so we'll pick up today here, and we'll take a look at the data from our textbook, which is on the Olympics 100-meter race time for the men's track and field event, and we can see that over time the winning race time has gotten faster and faster and faster. And so on and so forth. And I think the last thing that they recorded was 2012. So 2004, 2008, 2012, 2012. So they don't have 2016 or 2020. But anyway, this is what we have seen. And so we want to fit some kind of model to this, and we're going to just start off with a simple ordinary least squares regression. And on Monday, we showed that we can, set it up as a minimization problem, okay? And we said, if we define our things as W0 plus W1 x of n, you can have that summation term and do the derivatives, partial derivative with respect to the intercept and partial derivative with respect to the slope. And then you'll have a system of two equations, and you'll find where the partial derivatives, you set them equal to 0, and you set them equal to 0, you solve, and when you solve for that, you'll find the values of W0 and W1 that minimize the thing. What we're going to do today is we are going to work in linear algebra. I think I've shared this playlist, and I hope you had an opportunity to take a look at it. And if not, again, that's going to be your job this week to watch that playlist and refamiliarize yourself with a lot of linear algebra concepts that is a prereq for this class, but unless you took 115 very recently, you've probably forgotten a lot of this stuff. So what we're going to do is we are going to do linear regression, but we're going to frame it with matrix notation, okay? And the initial hurdle to get into matrix notation is a little bit cumbersome, or it feels like more work to do things this way, to learn something new. Anytime you have to learn something new, it feels like it's more work, but then you are thankful for having learned it, right? So, so what we have here is basically this is our linear model down here. We've got the intercept plus the slope times x. And we will write this as the product of our matrix W, okay? It's a column matrix with the terms W0 and W1 for the intercept and slope. And then we have a matrix representing our observation x sub n. And this is going to be the value 1 and the value xn, okay? And so this will be kind of the matrix. And so let's see. Sometimes when you're taking notes and stuff, like on the computer, I have the ability to do bold print, and you do not, right? So in your notes. So basically, you would just have to draw a little. Where's my markup tool here? I don't know where my writing tools are. Okay, let me. Basically, you just put a little vector arrow above it. Let me see if I can draw on this. Yeah. Everything is so hard. Okay, I don't know how to draw on my button's not clicking. Okay, I'll open up Paint. Because I don't know what else I'm supposed to do here. Okay, but basically, I can't even do this. Oh, my pen's just broken. That's all. No wonder. All right. Okay. This is so hard. I'm drawing with my trackpad. Okay, but basically, whenever you see the bold X, you'll probably draw something like this in your notes. Okay, and then and anyway, okay, that was sad. All right. Okay, but anyway, now we can express this type of equation with just this W transpose X of n. Okay. And then if we define a big matrix X, or big X, just the matrix X, as a bunch of these transposes, right? Little the vectors xn, okay, transpose. Then our matrix will look like this: 1x1, 1x2, so on and so forth, down to 1x of n, okay, for the last observation that we have. And then our outcomes, which normally we call y, but to try to follow the book notation, we call it t. Okay, we've got the vector t, or the column matrix. This is what we have, right? And what we can do is we can show that our loss function will become this. Okay, the vector t minus the matrix x times w, that whole matrix transposed times this resulting matrix, and I'll show it on the next few steps. Okay. I'm sad about my pen. I don't know. All right. So again, our big X matrix here looks like this, and our W matrix, the slope and intercept terms, show up here. And so when we do the product of big X times W, we get exactly what we want: W0 plus W1 x1, W0 plus W1 x2, so on and so forth down to the last observation. Okay, and so by just doing X times W, matrix X times the vector W, we get to kind of create a vector or a column matrix of all of our predicted or fitted values. Okay. Now, when you do matrix multiplication, for me, it's not always intuitive whether I should do X times W or W times X or things like that. Okay. And so what I like to do is I always like to write the dimensions underneath each matrix, and this helps me keep track of the order of the multiplication that needs to be done. Because matrix multiplication, you don't have the freedom of just rearranging the terms, okay? Because when you do matrix multiplication, the number of columns of the first matrix needs to match the number of rows of the second matrix in order for this to work, right? Because you do, this term times this and this term times this, and so if the number of columns over here does not match the number of rows, you're going to have this kind of dimension mismatch problem, okay? And so basically, our X matrix has n rows and 2 columns, okay? And then our W matrix has 2 rows and 1 column. And so when you multiply those two together, the inner dimensions, the 2 and the 2 here, must match, and they combine. And so the result will be a single column matrix that is n by 1, okay? And so I like to, in my notes, I like to write the dimensions underneath, and it's a bit of a pain to get the dimensions underneath in LaTeX, but it's here, okay? And so so I'll do this for a lot of these operations here. All right, so that's just the key. If for whatever reason if you do it the other way, W times X, it'll be 2 by 1 times n by 2, and then you'll see that the 1 and the n don't line up, and you'll have a mismatch problem. Okay. All right. So if we were to do something like this in R, we could extract out the value Olympic year as X. N is how many observations we have. and I can create a column of 1s by repeating 1 n times. This is actually unnecessary because R recycles, and I could have, but just kind of for this, I will create matrix X by binding this vector of 1s with the vector of X values into big X over here, okay? Again, creating this 1s vector is not necessary because R will automatically recycle. I could just type the number 1 here and do C bind 1 comma the vector X, and it's going to create a matrix, 28 rows, 2 columns. Okay, and then over here we've got the W matrix, which I'm just going to put in the value 1, okay, and make sure we have 2 rows and 1 column, and the dimensions of W is 2 by 1, and then so I can do the product X, and this is the symbol for matrix multiplication, percent star percent W, okay, and that will do the product there. So we have 28 by 2 by 2 by 1, and so the result will be 28 by 1. Okay. On the other hand, if I tried to do W times X, okay, W percent star percent X, I get this error. Error non-conformable arguments. This is probably going to be one of the most common errors you see this quarter, because we're going to be doing a lot of matrix multiplication, and if you put the order of the matrices together in the wrong way, you're probably going to run into this thing. And whenever you see this, the non-conformable arguments, it means that you're trying to do, 2 by 1 times n by 2 or something where the number of columns doesn't match the number of rows for this operation, okay? And so R is helpful, and it will tell you that when it tried to do this thing, it ran into a problem, okay? And so again, to try to solve that, if you run into non-conformable arguments, go on a piece of paper, write down the matrices that you're multiplying together, and make sure that the dimensions align, okay? And then rearrange your terms likewise, okay? So anyway, that's doing the stuff in R. All right, so we showed that X times W is going to be our predicted observations, right? Our predicted values, our fitted values, W0 plus W1 X1. This is what the model will predict for each thing. T is going to be our column of actual Y values, okay? And so, so this thing, T minus XW, all right, it looks like it's an operation, but whenever you see kind of these matrix things, try to think of this not as matrix T minus X times W, but just see this as the quantity that represents the residuals, okay? It's a little bit, you just kind of have to get used to recognizing that this is not necessarily a sequence of operations. It is a sequence of operations, but it also just represents the column of residuals, okay? Because if you think of this as a sequence of operations, you're going to think like this is more than one value, more than one column or something. It's not. We are taking the actual values T, our observed values, and we're subtracting off the fitted values, but that just results in one number itself also, okay? And so this is just going to be the column of residuals, okay? So T minus XW is this, all right? And again, just kind of show that, when you do addition and subtraction, the two matrices need to have the exact same dimensions, right? Otherwise, they're not going to combine, right? Unless you're dealing with like NumPy and you're broadcasting or something. But here we've got, n by 1 minus an n by 1, so that's going to result in an n by 1. You're just kind of combining those things directly, okay? So this is just a single column of values representing our residuals. And therefore, if I take that column of residuals and I transpose it so that it's a row, and I multiply it, do matrix multiplication by the column of residuals itself, we're going to effectively just get the squared residuals, the sum of squared errors, because in matrix multiplication, you're doing this term times this term times this term, and you're adding them all together. So, so here, this is 1 by n, okay? This row of T minus XW transpose is going to be 1 by n, and this column, T minus XW, has n rows and one column is n by 1. And so when I multiply those two together, we are going to get a 1 by 1 scalar value, okay? Which is exactly what we had when we did it kind of the old-fashioned way without matrices. Okay, so this term here, you know, t sub n minus w0 plus w1 xn, quantity squared, can be represented by t minus xw transpose times t minus xw. Okay, and so if we wanted to talk about our loss function, which is the mean squared loss, or the mean squared error, okay, we have n terms, and so we're going to just take that quantity, which is a 1 by 1 scalar, and divide it by n, or multiply by 1 over n, which is a scalar value in of itself, of course. So I just want to pause here and make sure this is okay, or if there's any questions here. All right, so this is what we're doing. And so now our loss function is represented by this, 1 over n times t minus xw transpose times t minus xw, okay? So this is the fun slide. And so if we wanted to multiply this out, okay, we can expand this, right? So you have to kind of think back to all of these transpose operations and how this works. So we've got t minus xw transpose times t minus xw. We can kind of distribute the t, the transpose operator, okay? And so this is going to be t transpose minus the matrix xw transpose times that. And then when you transpose a product, it becomes the product of the transposes, but you have to kind of reverse the order in order to keep the dimensions aligned properly, right? So if you think of what xw is, x times w is, x is n by 2 and w is 2 by 1, and so when you transpose them, x will become 2 by n and w becomes 1 by 2, and so you have to switch the order in order to kind of keep the matrix dimensions aligned. Okay, so now we have this, okay, t transpose minus w transpose x transpose times t minus xw, and in order to, and so to expand this, you just kind of do whatever, multiplication. Do you guys learn FOIL, first, outer, inner, last? Okay, that's exactly what we do, right? So we do the first terms, you know, t transpose t, that's the first, then the outer, t transpose xw, okay, and then inner, w transpose x transpose t, and then the last terms, right? W transpose x transpose xw. Okay, and then I went through the trouble of putting all of the dimensions underneath to just make sure everything lines up, because what we want is we want this to be a scalar value, right? When we do the squared errors, it should just be a single scalar value. So we have 1 by n by 1. Indeed, that's going to simplify down to 1 by 1. And we got 1 by n by 2 by 2 by 1, okay? And so I've got 3 of these matrices in a row. All that matters is that whenever you see the multiplier operator, okay, that the dimensions align. So I've got 1 by n by 2. Those n, the n here, the number of columns over here aligns with the number of rows, so we're good. And then we've got n by 2 by 1. The number of columns here aligns with the number of rows, so we're good, okay? And so only the outer dimensions remain, or the outer things remain, and so we get 1 by 1. Same thing over here, 1 by 2 by n by 1. Again, the 2's align and the n's align, and so that works out. And then here I have 1 by 2 by n by 2 by n by 1 for w transpose x w, okay? And again, everything lines up, which is exactly what we want. We have everything's a 1 by 1 scalar term, and so so this is what we have. And then we can actually combine t transpose xw and w transpose x transpose t, because if we look at these are actually scalar values, and they are just transposes of each other, okay? So t transpose xw is the transpose of W transpose X transpose T. I don't know if I'm talking too quickly, but this is the transpose of this. They are scalar values, so they're the exact same term, right? So they're exact same value, you can just combine them, right? It's just like saying, I've got the scalar value 5, and if I transpose it, it's the scalar value 5, okay? So there's nothing there, so you can just combine the two, and we have this, okay? So our sum of squared errors is now this term, T transpose T minus 2 times W transpose X transpose T plus W transpose X W, okay? And then again, if I want the mean squared error, then I just throw in a 1 over n term, and we're back to our loss function. Is this okay? I don't know if you guys are trying to furiously copy down notes or if we're just good watching all of this. Okay, it's a mix. All right. Okay, and this just says that I can combine those two terms, just so that when you're going through your notes, it's there. Okay, and so now we have this loss function, and what we want to do is we want to find the value W that's going to minimize this loss function. Okay, so our loss function represents the function that we are trying to minimize, our objective function that we're trying to minimize, and what we want is we're going to treat the observed values x and t, those are our observed values, and we want to find the set of parameters w that will minimize this function, okay? And so what we do in calculus is we take the derivative with respect to w, we set it equal to 0, and we solve for w. Okay, and that's exactly what we are going to do, but now that we're working in matrix notation, this means we have to do vector calculus. And I don't know if you guys have done any kind of vector calculus before or not. You're just going to get just a small taste of it, just enough for it to be okay, all right? Just to get us through what we need to do. So I'm going to take a moment to just kind of review derivatives, and then we'll talk about the vector calculus equivalent of a derivative, which we call the gradient, right? Okay, so in regular old univariate calculus, you've got a function of one that takes in one real valued thing and it maps it to somewhere else in the real space, right? And that's why we have a 2D plane. It takes an x value and it maps it somewhere else, okay? And so that's what the function does. And the rule about the function is that it can only map to one other value, right? Okay, and then the derivative of the function is, you add some kind of little epsilon or an h value, okay? And you see how much did that function change? Okay, so you say, what's the difference between f of x plus h minus f of x, and you divide that by the difference h, and you take the limit as h goes to 0, and that's going to be the derivative, okay? And we can rearrange this, so if I subtract off f prime of x over here, okay, and throw it into the fraction, I can say that the derivative is the f prime value that satisfies this equation here, okay? So this thing here is exactly the same as this, okay? But so that's what we have for the derivative, right? It's how much, okay? How much does the function change with respect to x if I just add just a tiny little h, and we want that h to be almost 0, okay? All right. So in vector calculus, okay, now we have a function of a vector, okay? So over here, our loss function, this is the loss, the total squared error, it's a function of w. W is our slope and intercept, so it's a vector. It's taking two values here, the slope and the intercept, but when you plug that into the function, it returns one value, a scalar value for the total squared error, the mean squared error, okay? You're just getting one value. So our function goes from n-dimensional real space down to one-dimensional real space. Okay, and so now we have basically the equivalent of f prime, but we call this nabla f, okay, or the gradient. Okay, this little upside down triangle, which looks like a delta, is called the nabla. I don't know, but anyway, we've got this. This is basically f prime. And so because we're, so if you look at this thing, it looks exactly like this, except everything is now vector terms. And we want, you know, as h, which is basically, you know, a little perturbation, just a little thing that you're adding, but now it exists in n-dimensional space, we're going to shrink that down to 0, okay, or so that its norm here, the norm of h, the magnitude of h, shrinks down to 0. And when we do that, you know, it needs to satisfy this equation. Okay, and so here we've got, this is what we have. Okay, so anyway, that's the gradient. Kind of to just make it a little bit maybe easier, we can think of the gradient with respect to some vector w at w is a vector, okay? And so if we've got n-dimensional space, all right, it's going to be basically the partial of f with respect to w1, the partial of f with respect to w2. So it ends up just being, so again, the function produces a scalar value, and when you take the derivative of that function with respect to a vector, you're going to get a vector, okay? So the gradient itself is going to be a vector, and it's basically the vector of partial derivatives with respect to each component in this vector w. Is that okay? All right, so, so my loss function produces a scalar value. It takes in a vector of what size? Okay, so this is what we have. It produces a single scalar value, a 1 by 1 scalar value, and it takes in a vector of size 2 by 1, because the vector it takes in is w. Okay, the intercept and the slope. And so if I take the gradient of L with respect to w, what dimensions will that have? 2 by 1, okay? Because w is 2 by 1, the gradient will also be 2 by 1. Okay? All right, and so this is just a note about the gradient, and this will become very important later as we start avoiding trying to solve equations, okay? So like the derivative, the gradient represents the slope of the tangent, you know, of the graph of the function, and more precisely, the gradient points in the direction of the greatest rate of increase of the function, okay? And its magnitude is the slope of the graph in that direction. So, so anyway, the gradients will be vectors themselves. Here's just kind of a helpful list. So when you have effectively some kind of vector multiplied by another vector here, okay, w transpose x, and you take the, so if the function is this, and you take the gradient, or the derivative with respect to w, you're going to get back x, okay? And if you have x transpose w, and you take the gradient with respect to w, you get back x. And if you have w transpose w, which is kind of like w squared, right? In matrix notation, w transpose w is like w squared, you get 2w, okay? So much like taking the derivative of x squared gives you 2x, w transpose w gives you 2w. And then here, if you have w transpose C being a matrix times w, okay, which is generally how you have to align the multiplication. So this is kind of like a constant times x squared. Then you're going to have 2 times, you know, that matrix C times w, okay. And so this is just kind of some helpful gradient relations. All right, so we will take a look at our OLS loss function, which is the mean squared loss. I've just distributed the 1 over n term. So I've got 1 over n times t transpose t minus 2 over n times w transpose x transpose t plus 1 over n w transpose x w, okay? So this is our loss function. It's currently a function of w, and we want to take the gradient, or basically the derivative of this with respect to w, okay? So we want to take the derivative of the loss with respect to the vector w, and we're going to set that equal to 0 and solve for w in order to find out where this function has a local minimum or maximum, or wherever just the gradient or derivative is equal to 0, right? So if w is a 2 by 1 vector, then the gradient nabla f must also be a 2 by 1 vector, okay? And so I'm just going to go through and we're going to say, what is this with respect to w? Okay, so the t transpose t, there's no w term in there, so the gradient with respect to that is going to just be 0. Okay, so it's much like taking derivatives in calculus, except everything now has arrows over it or is in bold print. Okay, so we've got derivative of this is 0. Here I've got w transpose x transpose t, so the gradient with respect to w will just become x transpose t. Okay, and if we think about what that is, okay, we've got x transpose is 2 by n, and t is n by 1, and we can see that this will result in being 2 by 1, which is what we want. Okay, and over here I've got w transpose x w. Okay, so the gradient with respect to w will be x transpose x w. Okay, which will give me x transpose is 2 by n, x is n by 2, and w is 2 by 1. Now some of you might look at this and say, well, why didn't you just do w transpose x and then take off this w? Why did you take off the first w and not this w? Okay, valid question. Again, it's answered by writing out the dimensions. So if I kept this w and knocked off this one, then w transpose is 1 by 2, and the resulting thing, if I had w transpose x will be a 1 by 2 vector, or 1 by 2 matrix, okay? Which will not work out, okay? So I need the result. You have to kind of see what are the dimensions that you need, and you kind of take the operation that's going to result in the dimension that you need, okay? So rather than eliminating the w at the end, I eliminated the w at the front when I took the derivative to make sure that the result ends up being 2 by 1. Okay, so this is what we have to when we're doing kind of vector calculus, and we're trying to think. You know, these operations are not hard. The hard part is figuring out. You know, I can you know, pull off this w or pull off this w. You have to kind of keep in mind what are the dimensions of the result that you need, and you do the operation that's going to give you that needed result. Okay. All right. Is this okay? And so now the derivative of the loss function with respect to w is this. Okay. The scalar constants remain. Okay, and I've got minus 2n plus 2n x transpose t plus 2n x transpose x w over here. Good? Yes, question?
So for the third term, it's like 1 over n on top and 2 over n on the bottom for the third term.
Oh. Yes, because I've got, this is basically what we have here, okay? W transpose times a constant, okay? W transpose times a constant x transpose x w, okay? Whoops. So I've got W transpose, basically this C here is X transpose X times W, all right? So that's what we have here. I've got W, X transpose X W, and the result will be 2 X transpose X W here, okay? And it's basically like having like 2x squared or something, and then you would multiply that. When you get rid of the square and the x, you multiply that, and 2x squared derivative of that will be 4x. And similarly, I've got basically, you know, that, okay? So it does go from a 1 to a 2 here. Yes, question?
So the 0 that like came from the t transpose t.
Yeah.
But like, so if we started with dimensions of t as n by 1, does it become like a 2 by 1 vector of 0?
Yeah, okay, so, right. So here, this is actually 1 by 1. T transpose t is 1 by 1. And so it's a scalar value. And again, when you take the derivative of a function with respect to a vector, its result will have the same dimensions as that vector. Okay? So this is a scalar. This is 1 by 1. But when I take it with respect to some function that's some vector that's 2 by 1, the result has to be 2 by 1. Okay? And so you're going to get a vector or a column of zeros that's 2 by 1.
Okay, thanks.
Okay? All right, and so we have the gradient, and we set the gradient equal to 0, okay, which is what we have. And then so I can just do addition, and I can get rid of the scalar values 2 over n, okay, which are equal. And so I have x transpose t times x transpose x w, okay. Now, when you're dealing with matrices, there's no division. There's no matrix division, okay? If you want to cancel out a matrix, you have to multiply it by its inverse, right? So when you take a matrix and you multiply it by its inverse, you're left with the identity matrix, okay? So that's what we have to do, okay? So here I've got x transpose t is equal to x transpose x w. And I want to solve for w. So in order to get rid of this, okay, I have to multiply x transpose x by its inverse so that the result will be the identity matrix, okay? So I'm going to multiply the right-hand side by x transpose x inverse, and I'm going to multiply the left-hand side by x transpose x inverse, okay? And so again, I just kind of have to make sure that the dimensions line up, which I've shown here. So this is x transpose and x transpose and t, okay? So if I do multiply both sides by x transpose x inverse, the inverse of x transpose x, and just think of this as a matrix. Again, not as a series of operations, but just think of this as the matrix that represents the inverse of x transpose x. We will be left with w, okay? And so you have w is equal to x transpose x inverse x transpose t. And this might be a familiar result, okay? And so that's what we have for the vector w that will minimize the least squares term, okay? And so so the w that's going to minimize the OLS regression is w hat, and that's going to be x transpose x inverse x transpose t. Okay, so here's just a very simple numeric example. I've got the values 1, 2, 3, 4, and the outputs are 1, 3, 2, 4. Okay, so they don't line up exactly. Okay, this one goes up to 3, and this one goes down to 2. Okay, and so if we plot that, it looks like this. And so I'm going to create the X matrix by binding 1 with X, and so I have 1, 1, 1, 1, 1. And x is 1, 2, 3, 4, and so this is my matrix 4 by 2, and we can do x transpose x, all right, and that will be 4 by 2. I'm sorry, 2 by 4 by 4 by 2, and that will give me this 2 by 2 matrix. X transpose x is this, and then I invert that. Okay, so in R, the inverse of a matrix is found by using solve. Okay, so x transpose x inverse gives me this. And if I do x transpose x inverse times x transpose, then now I have a 2 by 4 matrix, and then w hat is x transpose x inverse times x transpose t, and that gives me the estimates 0.5 and 0.8, meaning, whoops, This is a typo. The coefficient estimates is 0.5 for the intercept and 0.8 for the slope. I gotta fix that. Okay, so 0.5 for the intercept, 0.8 for the slope. Okay, if I used LM in R to just fit a linear model of x to t, it gives me back the same results, 0.5 and 0.8 for the intercept and slope. Okay, if you want to get your predicted values, you just take your x and you multiply it by that fitted matrix of w values, w hat. So I've got x times w hat, okay, because that's exactly what we get, w0 plus w1 x1, right? So we do x times w hat, and these are the predicted values, and I can plot that, okay? So I can plot a line with the intercept of w hat 1 and slope w hat 2, and we get this, okay? We can do the same thing with the Olympic data. The Olympic data looks like this. I can do a linear fit, which will give me this intercept and this slope. And then to create my x matrix, I just bind ones to the x column, and then I just do x transpose x inverse, x transpose t. This time t has to be a matrix made out of the Olympic times. And we get the intercept is 36.309, and the slope is negative 0.0327, which we can see is exactly what we got over here, okay? So, so indeed, running the matrix operations gives us the exact same thing that LM does, which is what we would expect. To get the predicted values from our model, we just do x times that w hat, and then again, we can plot that. And so we can just plot the year against the fitted values, okay? And we get the ordinary least squares regression thing. Okay, so this is all just doing OLS in matrix notation, and again, the idea here is we're just trying to find the values of W that minimize our loss function, okay? So still an optimization problem, just now in matrix notation. Okay, we'll end there.